Hi, and welcome to part 6 of Neurons 2. We start out with the role of myelin. Why is that myelin there on the axon? You have a diagram there of what the myelin sheath looks like. We know that neurons can be very long, up to about a meter. That's thinking of the axon. And that conduction, it's important for that to happen quickly. Action potentials should be traveling very quickly. So the speed of conduction can be increased or is increased by myelination. It's going to travel very fast along that axon that can be very long. Well, how does it do that? Well, it turns out that the myelination is a coating. Remember oligodendrocytes? And it prevents the leakage of these ions. It's kind of like taking a wire and putting a plastic coating on the outside, no different from a wire that you'd have coming from a lamp, where it's insulated, and that insulation is the myelination. This action potentials are going to actually jump, and I have that in quotes, jump, because it's not exactly jump, but it has been named that, and it's been named saltatory, which means to jump. Saltar is to jump. So saltatory conduction, because what happens, if I can show you on the diagram, is that they are this depolarization that's happening here, for example, and then this depolarization that's happening there, and this depolarization, do you notice, happening in those nodes, they're called nodes of Ranvier, between where the myelination happens. So it doesn't need to depolarize every section of the axon. It's going to depolarize here, and then it's going to influence this region here, which in turn will influence this region here, which in turn, and you get the story now. So it seemingly looks like this action potential is jumping along, but remember, this is very small, and those spaces are quite close together. So it's moving along, but it's moving along more quickly because it's not depolarizing it's not opening every single sodium channel. My best analogy is thinking of a field, a soccer field, and someone kicking a ball, with 1 or 2 kicks down the field rather than dribbling it all the way. It's going to be faster to have these couple kicks, pass it to one person, and the second person kicks it again. So that's what we call the saltatory conduction. Think of also that myelination is an effective alternative to large diameter axons. What's that mean? As animals got larger evolutionarily, you would have to make neurons and axons broader, of larger diameter and larger diameter and larger diameter in order to accommodate a larger animal for it to conduct at a speed that you want it to conduct. So instead of manufacturing or making or evolving neurons that are of a greater diameter, instead the trick is to myelinate, and that way you can increase the velocity of that transport, of that action potential. Large diameter axons increase the speed of conduction. So those are the 2 things that are going to tell whether a neuron conducts quickly. And it is, what is the diameter of the axons, and is it myelinated or not? So you can increase the diameter and it's going to make it go faster. Now, if you do both, increase the diameter a little and myelinate, that action potential is going to go fast. Most of them are of neurons in humans are myelinated because they need that speed of conduction. However, sometimes there is a degeneration of that myelin sheath. This is an autoimmune disorder, multiple sclerosis, where instead of looking like this, where this sheath looks very intact, you have the eating away at this sheath here. Do you notice here they did it with a dotted line? And what would happen there, notice how the sodium channels are here in the nodes of Ranvier, and this is deteriorated, and what happens in these regions then, instead of having an action potential that's just driving through here, it's leaking ions. And that current leak is going to slow down the conduction, and sometimes so badly that it doesn't actually reach the other end, which is sort of goes against our all or none, but that is in the case of MS, multiple sclerosis. Two questions arise next, and that is, at what velocity of a stimulus does a neuron fail to respond? What's that mean? It means how quickly can I send one after the next one, like shoot one and then another and then another and then another, and how quickly can I do that before it's unable to respond to those stimuli, because they come too frequently, one after the other. Okay, and the other one is, can an action potential travel backwards? And if not, why not? So we want to look at that. Can many action potentials, how many can you have in a millisecond? And then can they travel backwards? So this diagram from your book is a good diagram showing the flow in an active region first. Here, the active region would be in yellow. So what's happening in an active region is that it's depolarizing. So if it's depolarizing, sodium is entering the cell in that spot. Now, if you go immediately behind where it was coming from, right? This is the axon hillock here. If it's coming in this direction, and you go immediately behind that active region, there's a region where the potassium channels are still doing their thing. You know, sodium's already done it. It's already poured in and then stopped. But potassium is kind of still doing its job, and its job is to go extruding that potassium, getting that potassium outside of the cell. So imagine this entire region here is still working on the previous action potentials, correct? So we call that the refractory region, because there is no way that we can open a sodium channel right now when the potassium still hasn't finished doing its thing. Okay, so that refractory region is the region immediately behind where the action potential is sitting. So we call that active, and behind it is refractory. And what about ahead of it? Ahead of it would be an inactive region where nothing's happened yet. The sodium hasn't come in yet. But this charge difference is starting to depolarize this membrane here, and what's going to happen next is sodium will be able to come in. Okay, so think of those three regions always happening along the whole extent of an axon until it reaches the other end. The importance of this is that that refractory period maintains the direction of the action potential, because if I can't depolarize this refractory region, then there's no way I can start going both ways. Even though there's a charge difference from here to here, notice, look just here, and this charge wants to stimulate a change in these channels, it's not going to be able to, because the potassium is still doing its job. I'm going to read this here in step 5. The refractory period prevents backward conduction. The loss of potassium from the cytoplasm repolarizes the membrane. Now, there is an absolute refractory period where the sodium channel cannot reopen until activation and inactivation gates reset. Remember the resetting of the gates? So the absolute refractory period is, has that activation gate reset or not? And if it hasn't, there is no way you can have another action potential coming at that time period. You have to wait a little bit longer. No new action potential can begin, I'm telling you in the slide. And that's going to prevent the summation of action potentials so that you don't have one summating over the other one on an axon. They're going to be sequential. The second potential has to wait how long before it can actually fire again? Until it's reset and the activation gate has reset and the refractory period is gone and it can actually depolarize again. Well, that's 1.2 milliseconds. It's not very long, right? Milliseconds, 1,000ths of a second. So it's incredibly fast. But there is that little period behind the active section that cannot be stimulated by any means. So this chart shows the membrane potential, the absolute refractory period shown here, where an action potential is happening in red. The sodium has already done its depolarizing of the membrane, but look at potassium. Potassium is a slowpoke. I call it the slowpoke channel. Even though it got the stimulus at the same time here, it's taking its sweet time. And if it's taking its time, then there is this period here where there is no way that it can be stimulated, that axon can't be stimulated again. But if we wait a little bit longer beyond that 1 millisecond, do you notice? 1.2 milliseconds. In this section here, we're going to call that the relative refractory period. Because, yeah, not everything is reset back again. Do you notice? It hasn't reset yet. But there is a possibility of creating another action potential beyond that 1.2 milliseconds. So we're going to call that a refractory period, but just relative, because there is a condition that we could create in which, yes, we could stimulate that axon. Unlike this period here where nothing can happen. This graph is from your book where still I showed you the same graph, and then I showed you what's happening here with the channels. That's kind of hard to see, so I'm going to enlarge it for you. Imagine this sequence of events. At first, both channels are closed, sodium and potassium channels. So nothing's happening. Then the sodium channel is going to open. So sodium channels opened, and I have sodium coming in. And then sodium channels close and potassium channels open, right? Doing the things, but I've already closed the sodium channel. This is the absolute refractory period. You cannot re-stimulate it. But let's draw a line here. And now this is the relative refractory period where, notice how these channels, now the sodium channel has reset entirely. Remember that? Potassium might still be doing its thing, but once I have that channel completely reset, then we could again potentially have another action potential occurring at that time. But there's a but to that. What it takes is a very high graded potential. Let's get to that in a minute. So in describing the relative refractory period, I'm telling you the gates have reset, but the membrane has not yet repolarized. New action potential can be initiated, but it requires a larger stimulus to reach threshold. And the action potentials will have a smaller amplitude. Okay, I'm going to go back again. So in this region here, can it be stimulated? Yes, it can. Potentially it can. But what happens is that it's going to take a larger stimulus. It's going to take a louder sound, a brighter light, a greater mechanical stimulation. And also the action potentials will have a smaller amplitude. So this is an unusual situation where this happens, where these are happening more quickly than waiting for the entire action potential to finish. So in this case, the potassium channels I showed you were still open. The outgoing potassium is going to cancel out a little bit of sodium coming in. So refractory periods, why do we need this? Well, they're going to limit the rate at which signals can be transmitted, right? Can't overstimulate. And it ensures one-way travel. Action potential is going in one direction only. And that's a good thing. I'm going to stop this video and go on, begin this next, passing the signal on to the next cell is going to be the following video.